Building on what we did on the last lesson, I want to show you a proof of one of the properties of logarithms. So I want to start with this. If we say that m is equal to log base a of a and n is equal to log base a of y, then what's going to happen when we multiply these together? So what I want to do is first rewrite this in an exponential form. So this is going to be base a to the m equals x, and this will be base a to the n equals y. So if we were to multiply these out, in other words, if we said, what does xy mean? So given this information, x times y is equal to, x is equal to a to the m, and y is equal to a to the n. And you can see with exponent rules, that means that we have the same base. That's equivalent to a to the m plus n. That's one way to write it. And then we can take this statement here and rewrite it as a logarithm. So we could say we have, let's rewrite it all the way. So xy equals a to the m plus n. If we rewrite this as a logarithm, backwards from what we did here, we would say we have log base a of xy is equal to the exponent m plus n. Referring back to the definition of m and n, here's m and n. If we rewrite this part, so let's keep the left-hand side, log base a of xy, and instead of writing m, let's write what m is equal to, log base a of x plus what n is equal to, log base a of y. So we've essentially proved by starting with something, working through what we already knew about exponentials and exponent rules, that if you have a product of the argument, that's equal to separating the logarithms, keeping the same base, and making it into a sum. Okay, so that was our rule from yesterday. But this is basically a proof, in case you didn't push the I believe button, that the properties of logarithms work because they're exponents. Then this is another way to show it. So rewind this and watch it again if some of that seemed like black magic to you, because I wanted to actually make sense so you can remember those rules. All right, and then you've got some more practice today on expanding and contracting the logarithms. Let's just take a look at a harder example so we can see if we can make sense of how to do that. So this one's got composition of functions. It has a function, it's an exponential, inside of a logarithm, inside of another logarithm. How do we simplify this? So we want to start with the inside, and knowing that this is a base 10, I'm going to keep that outside part and work on the inside. I'm going to rewrite 100,000 as an exponent. So we know that it's 10 to a power. It's going to be 100 to be 2 zeros. So that's 2, 3, 4, 5 zeros to the 2x power. So this is going to end up being log of log base 10 of 10 to the 10th power. So what does that mean? Well, that means the base 10 raised to the 10th, what power we need to make 10 into 10 to the 10x, these cancel, and now this is simplified to log of 10x. So if we simplify this by expanding it, that's going to be log base 10 of 10. It's base 10 times x, so there's a plus there, log of x. Now we can say 10 again, raised to the 10, and 10 to the first, the log base and the base of 10 cancel, and now we have 1 plus log of x. So it looks like a ridiculously difficult problem, but it simplifies to 1 plus log of x. So this is the log of x, log base 10 graph, translated up 1 if we were to graph it, and There you go. This is the simplification for this problem. So hopefully that warms you up a little bit there. In this problem, we're trying to simplify with the properties of logarithm to write as a single term without a logarithm. So this has natural log in it twice. So let's think about this in terms of what it means to have a base with several exponents. So if you will, we're going to separate this way. This is e squared. And then if this is a negative right here, that means we have a base of e. We're going to do it like this. I'm going to go back here. This is a e squared. This is an e to the natural log of x. This is an e to the natural log of p. So in order to add and subtract, we have the base of e. And if I write it like this, I can separate it again and say this is e squared times e to the natural log of p over e to the natural log of x, because that's what a negative exponent does. It puts things in the denominator. So what do we have now? Well, natural log is an e as a base. So similar to this problem where we had base for the logarithm and an exponential, this one is backwards. So example 2 is backwards. I have an exponential to a logarithmic. So right here, the base and the base are the same. This turns into e squared times p. And on the bottom, e, and this is also base e, these cancel and we have x. So we've simplified these in two different ways. They're actually the same way, but the different order, because exponentials and logarithms are inverses. So they cancel each other out. They undo each other. So when we have an exponential, e to the power, and we have a logarithm, natural log of e, they undo each other and we just have p out. So there's two examples of some of the kind of problems that you have for homework tonight. Now let's look at applications of logarithms. So I have two equations written for you here on the left. One is pH, those are base 10, and also the Richter scale, which uses logarithms to define a magnitude of 1,000 times bigger than another earthquake or 80 million times bigger than another earthquake, but in a form that is reduced to numbers that are easier to think about and consider in a scale. So both of these use logarithms to take really large numbers and simplify them into scales of 1 through 10. First thing we want to look at is pH. So pH level, if you've ever been a lifeguard, you've had to check the pH level in a pool. So this is defined to be the negative log of the concentration of hydronium ions in units of moles per liter. So they say solutions with a pH less than 7 are said to be acidic, while those with a pH greater than 7 are basic. So pure water is here at 7. Things that are on this side, so less than 7, are acidic, and then going in this direction up to 14 are basic. So 7's right in the middle. So we're going to think about this scale in determining pH of things in some equations. So we're going to use log, which is base 10, and put in what we're told is the concentration of ions, and then it has to be opposite, so the equation has a negative in it, otherwise we would get negative values on our chart. So let's do some problems like this. Okay, you may have noticed orange juice on the chart that we just did. So our first example is, okay, if a sample of orange juice is determined to have the concentration of 1.58 times 10 to the negative 4 moles per liter, what is its pH? So to do that, we're going to use the equation of opposite, the logarithm of that amount. So pH is equal to negative log, and we put in the concentration amount. So 1.58 times 10 to the negative 4. If we simplify this using what we know about logarithms, we can say it's negative the log of 1.58. And then multiplication means that we're going to have plus log base 10 of negative 4. This value is, the whole thing is negative. So this value we're going to have to put in the calculator. So we would say log of 1.58, that's going to be 0.199. And then this we can simplify because this is base 10. So base 10 of 10 is going to be negative 4. These cancel. This comes down. And now I have negative 4 plus 1.99. So I'm going to say, I'm going to say this is a positive value. So plus negative 4 equals negative 3.8, which is equal to 3.8, which is why we saw it in the chart as 3.8. So let me find that chart again. So here it is. Grapefruit or orange juice is right here. So you've got some other things where you're trying to find pH. I think when you test it in a pool, you just do it by color and check a color chart, which is why this is colored so beautifully. But basically what you're doing is finding the pH level based on that concentration. Our next example is the Richter scale, which is also base 10 like pH. So the Richter scale gives us a way to have a 1 through 10 scale, which talks about the intensity of the earthquake. So you've heard of the Richter scale, obviously. Every increase of 1 on the scale means a factor of 10 in intensity of the earthquake. So let's look at this example. Here's the equation for it. It compares the intensity of this earthquake to the intensity of just 0, meaning just barely noticeable earthquake. And that's by, not by humans, but by measurements. And they give you a picture in the book of how they measure it with the little machine. So anyway, this example they give in the book, example 7, says in India they had an earthquake that was 80 million times as intense as a level 0. So it was in India. This was in 2001. They had one that was 80 million times as powerful as a basic sub-zero or sub-zero, I mean here, earthquake. So how do we calculate that on the Richter scale? So the equation is the Richter scale equals log of the intensity given. So this is 80 million. This is going to be 8 times 10 to the 1, 2, 3, 4, 5, 6, 7, 10 to the 7 over I sub 0, which is just 1. So the 1 comes from log base 10 of 1. That exponent has to be 0. So we're talking about here, 1 here. So this would be 10 to the 0 equals 1. There's a 1 here. So we are going to separate this out. We're going to say that this is log base 10 of 8 plus log base 10 of 10 to the 7th. So because there's multiplication here, we're going to separate it into addition. And this is easy to simplify. This is 7. And this log base 10 of 8 is less than 1. And I know that because 10 to the first power would be 10 here, and 8 is less than 10. So we can put that easily into our calculator. That's why it's base 10. We're going to say log of 8, and we get 0.903. That's 0.9. So this on the Richter scale is a 7.9 on the Richter scale. Okay, so there are a couple of formulas that scientists use to calculate things that you're going to be familiar with as we look at logarithms. The last idea that we want to cover in this section is change of base. So we've looked at different bases and the different graphs, but what does it mean to have a change of base in the calculator? And although we've talked about how this calculator has under math a log base equation where you can type in a different base, you can't see that. Here it is. So again, math, if you went up to log base, it gives you the log base, and I've done it twice now. Math, log base, here's the basic version of it. So you could do a change of base here in this calculator. But if you don't have a calculator that is this advanced, you need to know the change of base formula. And it's so easy that I want to show it to you. So let's say that we have log base b of a, and we want to write it so that we can calculate it with the calculator easy buttons. So those are the common logs, where we have log of x equals log base 10 of x. And if we had the natural log of x, that means the natural log of e, and then x is the argument. So we can change anything that has a base that's different from 10 or e into either of these that are easy to solve for. And I'm going to show you the change of base, how it works, and then I'm going to show you the easy way to just memorize it. So if we made this into an equation, log base b of a equals x, and we rewrote it as an exponential, then we can get the way to solve for this. I'm going to do this with some actual numbers. So let's say we're trying to solve log base 2 of 9 equals x. Okay, so our actual one that we're going to change the base. So pretend my calculator doesn't have a way to change this base to 2, and I don't know how to calculate this because 9 doesn't have a base of 2. So I can't do this just from logarithm rules. So, but what I can do is I can say this is equivalent to 2 to the x equals 9. So if I did hamburger helper, I get 2 to the x equals 9. And from there, I'm going to solve with a simple inverse rule. So because this is an exponent, if I take the natural log of this side and the natural log of this side, then with logarithm rules, I can say that this power can move to the front. So that's x times the natural log of 2 equals the natural log of 9. This is the first time you see me take the logarithm of both sides, but that's something we're going to do very soon a lot. Now, natural log of 2 is a number, the natural log of 9 is a number, and I've got x multiplied by this one. So if I divide by the natural log of 2 on both sides, this one cancels, and I have x equals the natural log of 9 over the natural log of 2. On the calculator, I can do that quickly. I can say natural log of 9 divided by the natural log of 2, and I get 3.170. X equals 3.170. If I use the log base, so math, log base 2 of 9, I get the same number. If I actually didn't use the natural log here, if I took the plain log base 10 on both sides, so that I would get an equivalent statement, which is log of 9 over log of 2, so that's a base 10, I still get the same number. So log 9 on the top divided by log 2 on the bottom, we get the same result. So the simple way to remember this rule, but I wanted you to see how it works, the simple way is to say that you can write it as the natural log of the one on top over the natural log of the base. So this one is higher, so it goes in the numerator. This one is lower because it's a base, it goes in the denominator. So the change of base is this simple, and I find this is actually pretty quick to solve for things without having to go find that log base. And so this is the change of base. It started with a log of base 2. Change of base means now it has a log of base e. But you could have easily said that it was also log base 10. You can do it log base anything. The change of base works for any of those examples. So change of base, you need to memorize this rule so that you can use it to simplify things or just write it as change of base. So if you didn't have a calculator at all, you could rewrite it here in order to solve for later. So that's written here, change of base. The base goes in the bottom. The argument goes in the top. We also have the pH written here and the earthquake intensity. So you have practice problems. Try those. Make sure to check your odds. Write out all the steps. Do not just go from the book problem to the answer. Show how you got from beginning to end for all your work. All right, thanks. Bring your questions next class.